Welcome. This is electrostatic potential and potential energy. And the first thing I've got to say is that you've got to be careful about separating these two names. Potential is not short for potential energy. It's a different thing. So far we have had, sorry, let me go back and get my pen. So far we had the force due to electrostatics, and that equaled K big Q little q over R squared. And then we said, wouldn't it be useful if we had the electric field, which was equal to the force per charge that I put there, but you don't need the second charge there. So that equals Ke times the mother charge over R squared. And we said this is like a contour map, and this is like, the pull of gravity, and etc., etc. We can talk about the potential energy of a point. And so we have potential energy. And we can talk about the potential energy per unit charge, and that will be voltage. So it turns out, as we're going to find out, this is going to be equal to Ke Q1 little q over R, and this is going to be equal to Ke Q over R. Now, this is, I got to do a whole bunch of explanations on this. This is taking point charges, and we're not always going to deal with point charges, etc., etc. So this is, I'm just doing some comparison here between, one charge setting up a field and another charge in the field, and the charge by itself. And one charge setting up a field and another charge in the field, and the charge by itself. So I'm kind of like drawing those comparisons. But, what you learn is whenever things are confusing, put them down side by side. And a few years ago I was complaining that my class still wasn't getting this section. And my wife said, it's a different class every semester. You're still not teaching this section very well, so you've got to go back and revise how you teach it. And for one thing or another, I realized that I was never putting these things down side by side, and the book doesn't put them down side by side. So let's just compare and contrast a bit. So this is big charge, little charge over R squared. So it's an inverse square based on two charges. And this is an inverse square relationship based on one charge, the mother charge. And this is inverse relationship based on two charges, and this is a inverse relationship based on one charge. Now, units help. This is in newtons. This is in newtons per coulomb. This is in, what's energy measured in? Joules. This is joules per coulomb. Can you see how the electric field is kind of like the abstraction of a force, and the voltage is kind of an abstraction of a potential energy? Yeah. The other thing I'd like you to think about is this in terms of gravity. Here's a planet, and here's me, and there's the force of me on the planet and the force of the planet on me, and that's the Fg. And if I want to know what the pull of gravity is at that point, I would call it my little g. Isn't that what we do? Little g is measured in newtons per kilogram. Isn't that like newtons per coulomb? So electric field is like little g. Little g is not 10 meters per second squared, it's newtons per coulomb. Newtons per kilogram. Yeah, that's the conversion. So draw that analogy. And then over here, well, this is like, what potential energy does that mass have at that certain height? And you learned MGH, It's actually not. That's potential energy difference. We'll get to that. But you add a certain amount of potential energy, and this is like, okay, at that point here, what's the voltage, which is like what is the amount of potential energy that a mass would have if you put it there. Now, we never talked about gravitational voltage, but we could have done. Yeah, the gravitational potential. We talked about gravitational potential energy. So this is a little bit of an unusual, little bit of a new term, but I'd like you to kind of like draw the analogies. And that's what I'm trying to do at the beginning of this section. I'm trying to draw the analogies. So I start off just talking about terms. I'm doing gravity versus electrostatic. Gravitational force is the force caused by the proximity of two or more masses. And electrostatic force is the force caused by the proximity of two or more charges. It's a little bit more complicated because we have positive and negative charges rather than just mass. With gravity, the forces are always attractive because we deal with mass, not antimatter. We deal with matter. But with charges, we have positive and negative charges available to us. So sometimes the force is repulsive and sometimes the force is attractive. So it's a little bit more complicated, but not much. And then we learned about little g, and we said, well, it's good to have a conversion, so newtons per kilogram. It's the force that a mass would feel if it was of a certain value at that point. Got a question? No? Okay. And so we have electrostatic field strength. And that is E. Looks much more grand. E looks much more grand than little g, but it's just the same importance. And then we had gravitational potential energy, and that was measured in joules. The energy stored in a mass by virtue of its position in a gravitational field. And we have the electrostatic potential energy. That's not voltage. That's U. That's potential energy. We've got to distinguish between potential and potential energy. And that is our energy by virtue of its position in an electrostatic field. And then we have gravitational potential. We didn't talk about it much. Maybe we mentioned it, but it's the energy per kilogram. So how many joules of energy will it take to climb that mountain? 500 joules of energy. Well, for me, 500 joules of energy. But my daughter's only half my mass. For her, it would be 250 joules of energy because she's got less mass to carry up the hill. That makes sense? So potential energy has its limitation because it's very charge specific. I can have a charge field. I can have electric field set up by a family of charges. My potential energy depends upon me, putting me in there. But supposing I want a map that works for all of us, I really want the equivalent of contour lines. So I can kind of gauge how much work it will be to climb that mountain. And that's what we do with potential. It's the energy per kilogram. You're 3 kilograms, multiply that by 3. If you're 5 kilograms, multiply it by 5. If you're 1,000 kilograms, multiply by 1,000. So, you know, the gravitational force is kind of like very fundamental, and the electrostatic force is fundamental. The gravitational field strength is a little bit more abstract, and the electrostatic field strength is a little bit more abstract. The gravitational potential energy is kind of fundamental, and so is the electrostatic potential energy. And the gravitational potential is a little bit more abstract, as is the electrostatic potential. The ironic thing is what we find is that the fields and the voltages and the potentials are really useful. It's like really useful. So we tend not to talk about forces. We can always figure out the force if we know the field. We can always figure out the energy if we know the potential. It's easy. Just multiply by Q. You know? So that's where we're going. Now, I'm trying to kind of like tune you in on equations. So look at these similarities. Good old Newton's law, good old Coulomb's law. And then little g and E. And then, well, this was a little bit, remember this for work? We said the amount of potential energy is equal to the amount of work done. And that was equal to the force times the displacement, but the displacement had to be in line with the force. So we used this dot product to help us with that. Do you remember that? Yeah. You might want to review it if you don't. And this equals minus G, M over R, and we get the same experience over here, and then we have our voltage, and we have those. The more time you spend with these guys, comparing and contrasting, seeing where they come from, recognizing, oh, that's going to be 2 charges and an inverse square. That's going to be 2 charges and an inverse. That's going to be 1 charge and an inverse square, 1 charge and inverse. The more time you spend separating them and looking at their similarities, then the easier it's going to get. Because what's going to happen is people make the mistake on this is they get the wrong equation for the wrong thing. And it's because they're not seeing the forest. They're getting lost in the trees and they're picking the wrong tree. So really try and stand back a little bit and get the overview. The math is not hard. It's just the language is new, and there's 6 very similar equations. Because what happens is, I'm going to jump that, what happens is that we have electrostatic potential, electrostatic potential energy, and we have electrostatic potential energy difference. And we have electrostatic potential, and we have electrostatic potential difference. So, oh man. And I want to remind us of before. Do you remember when we talked about gravity and we said, oh, potential energy equals mgh? And we said, well, here's our mass, and it's at the surface of the Earth, and here's our h. So that equals, 20 joules. And then we said, supposing a workman comes along and he digs the hole deeper. Does this guy now have more energy? And if it does, how does it get it? I mean, I'm doing something at that part of the universe, and I'm affecting something at this part of the universe. I mean, And what we realized is, well, it's not really U is equal to mgh. It's really delta U, the change in potential energy, equals mgh. But we decided to call that 0 joules, yeah? So then we said, well, where is 0 joules? And we came up with ideas. We said, it's at the center of the Earth. But if you stop the orbit, you fall into the center of the sun. I know how far that is away. But if I stop the orbit, I fall into the center of the galaxy. I know how far that is away. If you stop that orbit, you fall into the center of the local group. I kind of know where that is. But if you stop the local group, I don't know where I fall into. I can't find the lowest point in the universe. So I don't know where 0 is. And that stymied people until they recognized that this is just a ruler. This is just a ruler, and I might not know where the bottom of the ruler is, but I know where the top of the ruler is. The top of the ruler is when I'm sufficiently far away from other masses that they have no pull on me. Once they're not pulling on me, I'm at the top of the universe. Let's call that 0. So this is minus 10 joules. That's minus 20 joules. That's minus 30 joules. That's minus 40 joules. It's weird measuring potential energies in negative numbers, but why not? It doesn't matter. If I go like that, I've still gone up by 10. Whether I've gone from 30 to 40 or minus 30 to minus 20, I've gone up by 10. Final minus initial, positive 10. So I can move my ruler around, it still works. So, okay. I'm a little bit uncomfortable with that, but you know what? I'm going to recognize that sometimes when I want the potential energy difference, and there's sometimes when I want the potential energy at a point, and there's sometimes when I'm going to want the potential difference, and there's sometimes when I'm going to want the potential at a point. And so I have 6 equations. I have electrostatic force, electrostatic field, electrostatic potential energy. I have electrostatic potential energy difference and electrostatic potential difference. 6 equations. They all look somewhat similar, but they're not that hard. Then the other thing I'd like you to get ready for is I'm going to deal with situations where my electric field is uniform and situations where my electric field is not uniform. I'm going to use symmetries. So it's either going to be radially symmetrical, pretty much, or nice and parallel. And it's important that you don't get these two confused. So you've got to know which of the 6 things you're talking about, and you've got to know whether you're in a uniform field or electrostatic field, or a non-uniform field. And after that, it's a piece of cake. It's not that hard in the end. It's just knowing what's important, what's not important, and we'll talk about that next time, okay? I'll draw a line here, and we'll talk about that next time. So.